13.75 billion years ago, the universe began. Why? We don't know. 380,000 years after the Big Bang. It's a very precise number. You might say, how do you know that? Well, before that time, the universe was so hot that atoms couldn't form. So, you had a soup of electrically charged particles. It was just too hot for electrons to go into orbit around nuclei, so the universe was opaque to light. It was almost like a big glowing star, if you can imagine that. Imagine if I told you that our universe has been around forever, even before the Big Bang. It might sound pretty wild, right? Well, hold on to your hats, because renowned physicist Brian Cox is on board with this mind-bending idea. It's interesting, this idea that the Big Bang created the universe, that's what Einstein's theory says, that's textbook cosmology, if you like. But the current textbook picture is there was a phase in the universe's life before the Big Bang. If you define the Big Bang as the hot dense phase from which the universe appeared, burst forth 13.8 billion years ago, that phase is called inflation. What we think happened is that before that, the universe was accelerating exponentially fast. It means it was doubling and doubling and doubling in size. And the numbers are ridiculous. We think that if you started with a universe that was smaller than a single atom, then it would be bigger by a long way than the whole observable universe with 350 billion galaxies in it, in less than a millionths of a second. So, very rapid, exponentially fast expansion. When that stopped, all the energy that was driving that expansion got dumped into space. It heated it up and produced the particles of matter out of which we're made and all the things that we see out there in the sky. And that's what we see as the Big Bang. So, that sounds wild, but that's standard cosmology at the moment. The big question then is, well, what started the inflation? What stops the inflation? How long did the inflation go on for? The answer to that is we're not sure, we don't know. There are theories now that suggest, as I mentioned, that there may be more than one universe, and potentially an infinite number. It's a mind-boggling idea, isn't it? I should say one extra thing. If that's true, then some of those theories say that what we call the constants of nature, so things like the strength of gravity, the speed of light, the masses of the particles, can vary from universe to universe. Then you ask the question, well, why is our universe so perfect for life? Why do stars make carbon and oxygen, the elements that you need for life? Why is everything so beautifully balanced so that living things can exist? The answer in these cases is because every universe exists. Every possible combination of the laws of nature exists in different universes. So, the reason we see a universe that allows us to exist is obviously because we have to see a universe that allows us to exist. How likely is that? Well, the answer, if there are an infinite number of them, is it's inevitable because there's every possible kind of universe. I must stress that this is very speculative stuff. But the first thing I said about inflation, the idea that there was this exponentially fast expansion before the Big Bang, if you want to use that language, that's not speculative, that's mainstream cosmology. This idea that that may lead to multiple universes is more speculative, but it's still scientifically valid. And there are people who do research into that. This is an active area of research. It all stems from a theory put forward by none other than Sir Roger Penrose, who suggests that our universe is just one in a whole cosmic lineup. Penrose's theory shakes up our understanding of time and space by proposing that there might have been universes before ours, all part of an endless cycle of creation and destruction. Picture it. Countless universes popping into existence over unimaginable stretches of time. It's not about infinity with no beginning or end, but rather a series of beginnings and endings. So, what does this mean for our grasp of reality? Could it be that time itself doesn't have a beginning or end? It's a mind-bending notion, but one that's worth exploring. In scientific circles, Sir Roger Penrose is esteemed as a brilliant mind, with a reputation in the UK comparable to that of the late astrophysics luminary Stephen Hawking. Penrose holds a Nobel Prize and was knighted by the British Queen for his scientific achievements. One of his most controversial theories is conformal cyclic cosmology, which suggests that our universe may have originated from a previous one. This theory challenges conventional notions of time and space. Recently, the James Webb Telescope provided new support for CCC with discoveries that contradict traditional cosmology. Let's delve into the surprises revealed by the James Webb Telescope and what they imply for Roger Penrose's CCC cosmology. Alongside the 16 galaxies that existed so early in the universe that they must precede the Big Bang, 6 black holes also emerged, exhibiting similar characteristics just a few 100 million years post-Big Bang. These colossal entities already surpassed 1 billion solar masses. Then, a scientific revelation shattered existing explanations. The discovery challenges previous notions about the Big Bang's timeline. While not as ancient as other findings by James Webb, this galaxy, nearly identical to the Milky Way, raises questions about established theories. Although galactic resemblances are not uncommon, it took billions of years for our Milky Way to evolve into a fully formed spiral galaxy. This newfound galaxy existed approximately 2 billion years post-Big Bang. Assuming galaxies like this one require billions of years to develop, their age stretches beyond the Big Bang. This presents a unique advantage compared to James Webb's other discoveries because of its proximity. Analyzing the light of this galaxy is somewhat easier compared to the even older galaxies spotted by Webb. The data regarding the number of stars, their compositions, and the formations within this galaxy are more reliable. They indicate that this galaxy exhibited a level of maturity similar to our Milky Way only billions of years after the Big Bang. Have you ever pondered the idea that our Milky Way also existed in some form during the early universe? It could have been a small, irregular globular cluster at that time. Or perhaps our Milky Way is much older than previously believed and was already traversing space as a fully formed galaxy some 13 billion years ago. With an estimated stellar mass of approximately 3.9 billion solar masses, it's considerably larger than expected for galaxies of that age, although still relatively small compared to the Milky Way. However, the primary question regarding the evolution of galaxies in the early universe revolves less around mass and more around shape. The shapes of galaxies are believed to evolve through intricate merging and growth processes spanning billions of years. How does this recent discovery lend support to Roger Penrose's conformal cyclic cosmology? According to CCC, the universe didn't begin with a traditional Big Bang concept, but emerged from a previous universe with all information about matter, stars, and galaxies already existing. Despite this, each new universe in CCC still starts with an event akin to a Big Bang. Previous cosmologies struggle to explain what came before the Big Bang. Classical physicists claimed nothing happened, while quantum physics proposed a quantum tapestry of equilibrium. However, the origin of this quantum fluctuation remained unexplained until Penrose's idea offered some insights. The CCC is highly complex. So here's a simplified overview. Picture a universe much like ours, where massive black holes consume all matter. Eventually, as the last star and grain of dust vanish into these behemoths, physical forces halt. This initiates a chain reaction akin to the universe's demise for a brief period beyond our time frame. The universe reaches complete equilibrium, devoid of measurable forces or matter. Only the black holes may persist or evaporate. In this transition from death to renewal, eventually, a new universe emerges from what we might call a spark of life or, more scientifically, a law of cyclicity. Penrose's theory suggests that the universe's properties at its end closely resemble those at the beginning of a new era. He developed the CCC concept while exploring the core aspects of general relativity and quantum mechanics. To this day, the two disciplines remain considered incompatible. Penrose sought both points of contact and contradictions between them. In his exploration, he observed the significance of singularities and the characteristics of the cosmic microwave background. He noted that the thermodynamic time direction of the universe, as dictated by the second law of thermodynamics, could hint at a large-scale structure. Penrose posited that the universe likely originated in a state of very low entropy, indicated by the smooth and ordered state of the cosmic microwave background. Central to the conformal cyclic cosmology are the Hawking points, tiny regions within the cosmic microwave background that could be remnants of black holes from previous universe cycles. According to this model, these primordial black holes would have existed in an earlier universe epoch and subsequently evaporated through radiation, leaving behind observable traces in subsequent cycles of the universe. Another interpretation suggests that black holes managed to survive the transition from one universe to another. This perspective sheds light on why the discovery of ultramassive black holes near the Big Bang lends support to Penrose's theory. If information regarding stars, galaxies, and matter formation seamlessly transferred from an old universe to a new one, it's plausible that the evolution of matter and galaxies occurred at an accelerated pace. If the CCC theory holds true, it would establish a completely new starting point, prompting questions about the true nature of time and space. This notion aligns with the concept of the cyclicity of the universe, which serves as a coherent subset of eternal inflation and the multiverse theory. Naturally, this also prompts inquiries into the fundamental characteristics of time and space. The theory of eternal inflation traces its roots back to the contributions of physicists such as Alan Guth and Andre Linde. Inflation is a prequel to the conventional Big Bang picture. It provides a story that precedes the expansion of the universe, the formation of galaxies, etc. So, the way in which inflation explains the Bang is in terms of a very surprising feature of physics, which is the fact that gravity can actually sometimes act repulsively. Those of us who learned about gravity in high school and learned Newton's law of gravity think this sounds crazy because Newton's law of gravity is purely an attractive law of gravity. However, that changed with the advent of Einstein's theory of gravity, which is called general relativity. According to general relativity, gravity normally acts attractively, but there are circumstances under which it can act repulsively. Furthermore, modern particle physics very strongly indicates that at very high energies, we expect there to exist states of matter that would produce the repulsive form of gravity that general relativity allows. Inflation is basically the proposal that the bang of the Big Bang, the driving force behind the expansion, was this repulsive gravity as allowed by general relativity. Once you decide that this mechanism of propulsion is very likely the way our universe was born, you can ask what kind of universe it predicts, and if it agrees with what we see. In fact, it allows us to understand three very important properties of our universe. One is the uniformity of our universe. The cosmic background radiation, measured with incredible precision, has fluctuations that are incredibly interesting but incredibly tiny, only at the level of 1 part in 100,000, to an accuracy of 1 part in 100,000. The cosmic background radiation we see has the same intensity in every direction we look. The universe is unbelievably uniform on large scales, and that cannot be understood in the conventional Big Bang picture. Inflation explains it very naturally. In the 1980s, two researchers uncovered that following the Big Bang, a small portion of space experienced rapid expansion driven by a phenomenon called inflation. This inflationary period smoothed out initial irregularities, giving rise to the observable universe. However, the theory of eternal inflation suggests that this process never entirely ceases. In certain regions of space, inflation halts, forming bubble universes, while in others, it persists, potentially generating an infinite array of universes. This concept leads to the notion of a multiverse encompassing countless universes with varying physical laws and constants. Within this framework, there could be further inflation occurring as the bubbles expand, contributing to the growth of the multiverse. Where universes interact and inflation decelerates, overall, the multiverse is depicted as a realm of continuous evolution and creation. Amidst these processes, the concept of a cyclical universe emerges, emphasizing constant renewal and expansion rather than a definitive beginning and end. On a much larger scale, you can picture it like Earth. Earth is now our multiverse, teeming with billions of people, countless animals, plants, and diverse habitats. Within this vast expanse, individuals, animals, and seasons come and go. Yet, new life is continually emerging, making this world a vibrant expression of existence and growth. The concept of eternal inflation and the multiverse fundamentally alters our understanding of time and space. In the theory of relativity, time and space are viewed as components of a four-dimensional continuum influenced by the presence of mass and energy. While we've derived many scientific principles from this framework, we may have overlooked crucial aspects, leading us to the limits of our current tools. Will we discover the elusive theory that Albert Einstein tirelessly pursued throughout his life, the singular equation that encompasses everything the universe comprises, its origins, and its mechanisms? Despite Einstein's efforts, this ultimate equation remains elusive. Scientists continue to await the discovery of this mystical formula, often referred to as the unified field formula or simply the field formula. Maybe our mistake lies in focusing on a field too narrow to encapsulate something much broader. Just as we can't describe a tree by examining a single leaf, attempting to reconstruct the entirety of the tree from a leaf's genome in a laboratory might parallel current efforts in particle physics. Scientists aim to glean insights into the overarching mechanisms from the behavior of the tiniest particles. However, this endeavor is only partly successful. As the deeper we delve into the realm of subatomic particles, the more enigmatic our measurements become. Despite peering through telescopes across a vast expanse spanning over 90 billion light-years like James Webb, capturing light that has journeyed for more than 13 billion years, we must acknowledge that our observations may be akin to a single grain of sand on a vast beach. What role did black holes play in the universe's formation, and is it possible that they were the universe's inaugural entities? The scientist Neil deGrasse Tyson offers his own intriguing perspective on this matter. According to Tyson, we are part of this universe, we are in this universe, but perhaps even more important than these two facts is that the universe is in us. We stand on the brink of uncovering answers to some of humanity's most fundamental questions. Where did the universe originate? Who or what brought it into existence? Do we exist as part of a grand design or merely as a product of chance? Neil deGrasse Tyson, a distinguished astrophysicist and popular science communicator, suggested that the James Webb Telescope has detected indications of black holes from a previous universe. If this assertion proves true, it could imply that our universe is just one in an endless series of cosmic rebirths. Should this hypothesis be confirmed, it would necessitate a re-evaluation of the entire history of cosmology.